Hello, everyone. This is Liyi speaking for the Spex team from Japan. First, I would like to thank organizer Adam and Randall for all the great effort for getting so many people virtually together from around the world. And in this talk, I would like to introduce the atomic and the software update in the new Spex release, which just became publicly available a couple of weeks ago. Spex is a plasma code developed at Esslon since 1982. It is developed to handle X-ray spectrum, in particular high-resolution spectroscopy for many kinds of astrophysical conditions, collisional plasma from diffuse objects, the stellar corona, photonized plasma from compact objects, absorbing spectroscopy, charge exchange plasma, etc., etc. Just like AtomDB, Spex is supported by a very large database of atomic processes, wavelengths, rates, transitions of around 400 ions from hydrogen up to zinc. But it is slightly different from AtomDB that Spex is basically running on the fly, which means the model spectrum is calculated in real time directly from the basic atomic data, which is actually the ideal way to model, for instance, a nebular plasma model with a finite density, in which we need to solve the dependence both on plasma temperature and density. New Spex is updated now to a version 3.06, is mainly in this aspect. We have now a new calculation for the L-shell complex, RNL complex atomic data. Here you can see the plot showing the Spex version 2, also called the Mako code, calculation of a 0.5 keV CIE spectrum, and the latest model in the new release. You can see the new model is significantly different, or say improved, from the old one. This also will tell us that the Mako code has become out of date and probably should not be used for high-resolution spectroscopy. And we also have a new calculation for the cooling function in the photonized model and for the cooling flow model as well. We are happy to release a new Python interface for Spex. Yes, now you can run Spex efficiently in Python program. Finally, we have added about 20 new dust candidates in the dust extinction model. So I go to details. First, overall, the new Spex contain a better INL shell spectrum. We are now using a more accurate and more complete database. For the lower levels, we are using the RMH's calculation of collision strands from the ADAS team, which I think Yongji Mao is going to talk a lot more details later. Meanwhile, we also calculate ourselves all the resonance and the direct excitation channels using the distort wave method for the higher levels, which are not available with the R matrix. And besides the collision strands, we have also included all the necessary dilatory combination and auto-annihilation channels up to very large principal quantum numbers. While for the best measured transition in the lab, the sodium-like and the neon-like iron, we're now using the cross-section directly taken from the lab measurement. We have also found several wavelength errors in the real observation, and we have fixed these problems. A well-known possible issue in the theoretical rate is there are often reports of difference between the distort wave and RMH's calculation of the collision strands, which are now the two main sources of data used in the new RNL model in Spex. It is theoretically expected that the R matrix is more reliable, but distort wave is obviously needed as R matrix can handle in maximum a few hundred levels, while we in Spex, we have typically more than 1,000 or several thousand levels per ion. So we have systematically compared the distorted wave-based and R matrix-based spectrum, and here I showing 4 ions at temperature of their peak population. For the main strong transitions, we can see that the fully realistic distorted wave method, even with just isolated resonance calculation, can reproduce the R matrix spectrum within the 10 to 20% difference. while for those weaker transitions, it is possible that the discrepancy become larger. And these theoretical difference are actually also interesting candidate for the lab measurement. It has been a long history in the laboratory measuring this electron impact process of iron L complex, in particular the sodium-like and the neon-like iron. And a recent revisit to the problem is done at Heidelberg using the flash EBIT, which is a very efficient machine measuring the collision strength in low-density corona-like plasma. Flash EBIT have a 5 eV resolution at excitation energy, also called electron beam energy. It resolves the DR resonance up to principal quantum number n equal 10 or even higher, and has a very high counting statistic, which allow us to distinguish those weak resonance peaks from DR and the resonant excitation from the direct excitation continuum. And you can also resolve the resonant peaks up to say n equal 10. A lot more detail will be given in the next talk by Xingdang Xia. Here I only emphasize we are using the flash EBIT results for Spex. So this shows a little part of the data, and a problem here is we need to distinguish the DR resonance from the neighboring resonant excitation peaks, which are blended in X-ray, also called de-excitation energy. And we also have to restore the flux at the detector response tail far from their peaks. So we model the EBIT data into dimension based on the instrument response function. And you can see in this figure, this 2D method can spatially decompose the data into a set of resonant peaks for different process, and also the continuum direct excitation component. And this decomposition is not very easy with the classic 1D method. So by picking up the pure DR resonance, we make this plot, which is a direct comparison of the Spex spectrum, the old one before any correction, with the EBIT measurement. And note that this is not X-ray spectrum, this is a spectrum in the unit of excitation or electron beam energy. It is now clear that the data, atomic data in the old Spex will underestimate the DR strength at high principal quantum number of n equal more than 5. And in the new version, we have fixed this problem by using directly the cross-section measured with the EBIT. And this is the first time that the experimental excitation and DR rate are incorporating Spex. And we also did the same thing to the resonant excitation and the direct excitation components. Okay, now let's take a look at this classical plot. The neon-like iron 3s at 17 Armstrong to 3D at 15 Armstrong line ratio plot as a function of the CIE temperature. And we all know now that one of the sodium-like iron DR line is blended with a 3D line for the observational resolution. So obviously this line will also affect the line ratio. So we have updated the classic plot by taking into account also the DR line. And this becomes an astrophysically interesting line ratio, as it's being quite relevant to a range of science topics for the stellar corona, for the galaxies, and for the clusters. For the neon-like iron itself, the 3s to 3D ratio is increasing towards low temperature, while the DR line from sodium-like become more and more important at low temperature, so that the overall 17 versus 15 line ratio bend over eventually. And this is shown in this black EBIT curve, which is now incorporating in the Spex. And we also see the theory curve in red. Doesn't look too bad, but if you go to details, you can see the theory curve is off from the experimental rate for both the sodium-like iron and the neon-like. And it turned out that the theoretical bias for the sodium-like and the neon-like iron are on the opposite direction, so it partially canceled out. And the discrepancy between Spex and APEC at low temperature is mainly from the sodium-like iron DR. So we have also plotted many astrophysical observations from the stellar corona, elliptical galaxy, and groups. And most of these are found above the EBIT curve, which should be partially explained by the photon scattering and reprocessing at the 3D curve. It will become interesting now to see how our update affects the science in general. A straightforward approach is to use our new model to fit a standard spectrum, which now we pick Capella. Capella is a standard calibration source for atomic physics and also for instrument performances. In a recent paper, we used all the available Chandra HETG data of Capella, build a sophisticated multi-temperature modeling with all kinds of astrophysical corrections and manually take into account several known calibration issues. And from the final C static, we can see the old Spex and APEC have similar performance, and the new Spex is kind of doing a better job. The impact on the iron abundance is also significant, but honestly, even with the new Spex, we cannot get a formally satisfactory fit. And in the left, you can see a small part of the Capella spectrum. When looking to detail, you will find the new Spex are doing a decent job for the strong lines, while we still have a lot of problem with the weak transitions. The weak line are very challenging, and we still need a lot more works with more advanced calculation on the experiments to solve those problems. So after we have put in Spex some model calculation of the collision rate, we realize that it will have impact on the total cooling, in which the electron energy loss by collision excitation is an important ingredient. Yale's PhD student Liyi has been working on recalculating the cooling function and the cooling heating balance with the recent update of the atomic data. In the left plot, the new calculation of the total cooling curve in black is compared with the classic one in blue. You can see a difference at around 10 eV is mainly contributed by the change in the direct resonant excitation cross-section of several carbon, nitrogen, and oxygen ion. We have noticed difference in our new calculation of the cooling function and those in the cloudy and the atom dB curve around 3 eV, where the main cooling ion will become the atomic hydrogen, and we'll show that in the next slide. By incorporating the new cooling function, we now have a different solution for the stability curve of the photonized model, and we also have a new spectrum for the cooling function, cooling flow model. So as I have said before, the atomic hydrogen Lambda alpha 1s2p transition is now the main cooling ingredient at 2.5 eV, where our new calculation of the cooling function and the cloudy curve does not agree very well. And we found that the existing collision strength calculation do not converge for this simplest transition of the simplest atom. In particular, for energy below the excitation threshold around 10 eV, while the resonance and the radiative damping effect become more important. And recently, we found a laboratory measurement down 30 years ago is in favor of the colorway and also the Anderson results at around 10 eV, which should be here, near the excitation threshold. So this is an important message that for us, and also we are interested to know what happened to other energy, in particular for this 2.5 eV, where the cooling is important. Anyway, we are still discussing about it, and maybe we are going to change the rating specs in the future update, so we can have a better agreement in the cooling function with other code. In Spex, we also have absorption model for measuring the molecular and dust in the ISM. A lot of more new data has come recently from the work led by Essilor scientist Elisa Contini and colleagues. They measure a sample of compounds with different chemical compositions in the synchrotron B-line facility and obtain the extinction profiles, which are eventually implemented in Spex. We have already a lot of molecular candidates in the ARMO model. Now we have 20 more dust candidates, some in amorphous and others in crystalline form. A lot of them are measured in more than one edges. And on the right, you can see some simulation using Astina and Crisen response file. They're based on the gas model, and they are compared with the dust model using the measured cross sections. So obviously, our new model, such kind of model, needed for exploring the dust molecular composition and astrophysics, astrochemistry of ISM using the new instrument. In the new update, we also include the Python interface. It is still an ongoing project. Now it has a kind of experimental version. We still have a long way to go to catch up with PyAtomDB, but basically it is now possible to do some simple job like passing the command from Python to Spex and to return the results from Spex to Python and to make plots and so on. Now Spex has become more interactive, programmable, and perhaps more user-friendly. Yellow the platform as long as developing new functions that will be added to our future release. In our new web page, you are able to find some basic examples and demonstrations about PySpex, how to read data, how to fit, how to make plot, how to ASCII out, etc. Please go find yourself and have fun with PySpex. As a summary, basically we're now on our way to the launch of Crisen in 2022 or 2023. And the Spex development is also at a kind of intermediate stage. We now have a whole new set of IronL data ready, for which we have run a whole set of theoretical calculation. We have extra cross-section from the EBIT experiment, and we have also verified with the Capella spectrum. A new cooling function for pion and cooling flow model are implemented. And our dust model AMO has become even more powerful than before by incorporating more lab measurements. We welcome everyone to try our new Python interface, test it, and give us your feedbacks. For a future plan, by future I mean by the launch of Crisen, we will have more updates in the L shell, in particular for nickel, silicon, magnesium, and calcium, and we will revisit the K shell, iron K with laboratory data. The spectral model uncertainty is perhaps another item to implement, and tomorrow I will have another talk focusing on that. So please stay tuned. That's all I have, and thank you very much.
Wonderful. Thank you very much. You can imagine the thunderous applause that's virtually occurring. We have two comments. Well, from me, have you considered the converged close coupling calculations by Igor Bray et al. For the hydrogen 1 case?
I think one of the curve is close coupling method, which I think is similar to the one you mentioned, probably.
Ah, okay. Yeah, that would make sense. I don't recognize all of his collaborators.
Yes.
Okay. Okay, we have a question and comment from Greg. The sodium-like line that blends with iron 17 3D measured in link at Livermore at LCLS with flash and at Petra is a direct excitation satellite. Is there also a DR line that blends with 3D, or does that line have a large DR channel?
So I think it has a mixture of direct excitation and also DR. So if you look into the EB spectrum, the DR line of sodium-like is on this line. You can all see these DR peaks, and that should blend with a direct excitation continuum from the neon-like. So I believe the DR contribute to the 3D line.
Okay,
Well, you will see more from the Xintang's talk as well.
Yes, absolutely. Very much looking forward to that. Another question from me, you noted that you had adjusted your iron 17 excitation cross sections to match the laboratory measurements. We have been considering that for AtomDB, but have been concerned about the possible correlations between those two. The work that Stuart Locke and Adam have done suggested that the atomic calculations themselves suggest that if one of those is wrong, the other one might be wrong as well. How have you dealt with that problem?
I'm sure that this correlation existed, as that must be important for us to consider, and that must coming from some origin of physics in the theory. So that's I think we cannot answer that with just experiment, but for the moment, we would like to solve the problem in another way. I mean, using the laboratory measurement directly is useful way to give a correct answer to the rates, to the line ratio. Well, so, and the neon line is definitely the best measured in the lab. It has been done so many times with different configuration and also at different energy, and we could do our self-Maxwellian lines, so we can get the rate just like those calculated in theory. So I think for the moment we have solved this in this way, in experiment way, and we would like to consider the correlation study later.
Okay.
Thanks.
Thanks. And then one last question. We had, it's sort of related from both Chris Doan and Richard. Chris is asking, how is it that we can get the collision ionization so wrong? And so this is related to the issues both you and Adam had brought up. And Richard notes that presumably similar problems exist with respect to optical spectra, yet our optical colleagues still quote small errors on abundances, temperature, etc. Can you comment on how different the situation is in the two bands between optical and X-ray?
Well, this calculation of atomic hydrogen is not easy. Actually, I think Jungji is going to talk a bit, but basically it is harder than the atomic, than the hydrogen-like iron, definitely. And I think optical people has been using the collision strength of perhaps the Colorway and Anderson et al. Because this is, I believe, some of the reliable value for them. So actually in the beginning, we're also quite surprised to look at this because indeed, we did not expect this to be so different. So for the moment, we did not get a final answer, final theoretical answer to the difference. Where it's coming from, we know it may coming from some of the corrections in relativistic correction or damping correction, but still we want to solve this problem. This is a kind of ongoing project.